My name is Tommy, and this summer I was given an opportunity to research a hypergraph lifting map with Dr. Mark Budden from the math department here at WCU. First of all, I'd like to thank the SURP program for funding my research. A hypergraph is a mathematical object consisting of vertices and edges, and they give mathematicians a way to study how things are connected. Each edge contains a certain number of vertices. This number is called the uniformity of the hypergraph. The uniformity is usually given by the letter R, and if a hypergraph has a uniformity of 2, we generally just call that hypergraph a graph or a simple graph. Our lifting map works like this. First, we select our vertices in a graph. If they form an odd number of red edges, then the resulting R uniform hypergraph will have a red edge connecting those vertices. If, on the other hand, the original graph has an even number of red edges, then the resulting R uniform hypergraph will instead have a blue edge connecting those vertices. We examined this mapping over the course of the summer, and using both algebraic and combinatorial techniques, we obtained several results, one of which I would like to share with you now. Given an odd R, which is less than n, any coloring of a complete graph on n vertices, where the one colored or red edges form a complete bipartite graph, is a member of the null space of the mapping that we've been examining. Now, this sounds a little bit complicated, but really what it means is if we have a complete bipartite graph, which is just a type of graph, then under our lifting map, we will always end up with a completely blue hypergraph. We use this result to prove additional theorems in our research once we had this one. Complete bipartite graphs are important in the field of graph theory for many reasons. One of which is that they generally cannot be drawn in a plane without the edges overlapping. This is known as Kuratowski's theorem. Because of this, one application for complete bipartite graphs is circuit board design. If an engineer first models their collection of transistors and microchips as vertices in a graph, then they can see if they are forming a complete bipartite graph with their design. If so, then they have to redesign the board because it just simply won't work. Graphs and hypergraphs are used in many fields of study, including algorithm analysis, social networking, and even carcinogenesis research. Understanding how to relate models where connections are drawn between differing numbers of objects is imperative to understanding those models themselves. And that is at the heart of what I've been researching this summer. Thank you.